Hi, I'm Blake, and welcome to the Physicist's Guide to Success. I hope everyone's been doing well and staying safe from the coronavirus, but besides that, let's hop right in today. So one of the last labs I had in my first semester of calculus-based physics was a rocket lab, and we used the impulse momentum theory, which is what we're going to be deriving today. And it's a pretty simple derivation. It comes from Newton's second law. So we just start here, right? Second law. But then we just convert a to its derivative form, which is dv dt. Then we actually pull m into this. So like, let's pretend m doesn't have to change with time, but we just pulled it in there just because we can. If it's a constant, then it can pull it out and put in willy-nilly. But let's pretend that we wanted to group mv, and we'll call it p. So f is equal to dp dt. Then we integrate both sides by dt and end up with this. And let's pretend we didn't want this to be an indefinite integral. We wanted it to be a definite integral from time 1 to time 2. So it's going to be p at time 1 and p at time 2. And so then this ends up leading us to f delta t is equal to p2 minus p1. So in other words, f of delta t is equal to delta p. And this is the impulse momentum theory. This p right here represents the momentum, and this represents the impulse. When you really think about it, it shows that like the force acting on a certain time period is equal to how much faster that object is moving, if you kind of see what I'm saying. And that makes sense. Like, let's pretend you're pushing on an object and you push really hard. It's going to change. This force is going to be great. And then this momentum change is going to be greater too. You're going to be forcing the object to move quite a bit. But if you didn't push that hard, this would be really small. And this would be small too. And then the object won't move as much. And that follows intuition. So oftentimes when we use impulse momentum, we're going to be talking about collisions. Sometimes you don't. Like in the rocket lab, you wouldn't be really talking about a rocket colliding with anything unless that's your goal. I don't know why that would be your goal, but who knows. But let's pretend we're talking about collisions, like car crashes, or even something more simpler, like pool balls hitting together on a table. Well, we'd often have P1 initial plus P2 initial is equal to P1 final plus P2 final. And this is basically saying that the momentum in the system is conserved. Usually, this is not the case, because in order to state this statement, we have to have one vital thing, is that the system has no external forces, where the net external forces on it is 0. And usually that is no problem, because if you're dealing with something like gravity, it's going to be canceled out by the normal force, so it's not going to be that bad if it's on the ground at least. What this usually is a problem is if there's something like friction. Like let's pretend there's a box here. This is going to be, why am I drawing so bad? This is the normal force. This is mg, and this is friction. Well, if we see here, the net force here would actually, if this wasn't colliding into the ground and like being absorbed into it, the normal force should cancel out mg. So that means that there'd be no external forces in the y direction, but if you look in the x direction, nothing's canceling out that friction. That means there is an external force. So we can't say this right there. So usually too, when you look at giant crashes or real world crashes, it's really hard to even use the statement because you don't know if it's true. You don't know if the momentum is actually conserved, because what if they just things can happen if there's friction. Everything changes, and this doesn't really become as useful if you didn't really predict an accurate result. But there are two special cases in which it does work. The first is when kinetic energy is conserved. So we learned that in the last chapter. It's going to be, kinetic energy is. It's going to be K1 initial plus K2 initial is equal to K2, or why did I say K2? V1 final plus K2 final. So if we have these things here too, then we can actually couple this and make a special equation because, sorry, I didn't mention this earlier. This is actually a really hard equation to solve because you have two unknowns, right? Because if you know, usually no problem, because if you measure the masses and then you also measure how fast they were going, well then you might have two masses here, but then you also have two unknown in how fast they're going. So you need to either be given 5 things that are known, or you need to be given another equation to use. Because before we go any further, let's list the things that are actually unknown in this. So it's going to be M1, M2, V1 initial, V2 initial, V1 final, and V2 final. So if you know all the initial stuff, well, let's pretend you had a speedometer and then you're just like tracking 2 cars and then you rate the cars beforehand and then they crash and you wanted to predict that. Well, like let's pretend you're an experiment or something. Well, you wouldn't know these 2 things. So you need to get another equation. And that's where this comes in. So if we say that kinetic energy is conserved, it's called an elastic collision. Think of 2 pool balls colliding. It's going to be going here, and then there's another ball, and this one stops. So essentially, kinetic energy is going to be restored. Nothing's being converted to the environment. There isn't any crumpling. Like the pool balls don't crumple, they just bounce off each other. That's what kinetic energy is. So there's no energy really being lost to the environment. If we do say that, then we can actually combine these equations. So we have, let's just rewrite everything. M1 V1 initial plus M2 V2 initial is equal to M1 V1 final plus M2 V2 final. And if we actually sort this out and bring the M1 terms to one side, it's going to be M1 V1 initial minus V1 final is equal to M2. Why am I doing an integral sign? V2 final minus V2 initial. But if we look at here on the, I'm sorry, I'm pointing out my notes. If we look at the kinetic energy equation, it's going to be M1 V1 initial, taking out the 1/2 from both sides. M2 V2 initial squared is equal to M1 V1 final squared plus M2 V2 final squared. Well, if we move all the M1 terms to one side like we did before, it's going to be V1 initial squared minus V2 final squared is equal to M2 V2 final squared minus V1 or V2 initial squared. And this is actually just the square, I forgot what it's called. It's just the something of differences. The product differences, I think. Well, anyways, all you need to know, if you remember this from what is it, algebra or whatever the union of quadratics was, it's going to be V1i minus V2f V1i plus V2f, and you can go in and expand that out, but that's what it becomes. And V2f minus V2i V2f plus V2i. Sorry, I kind of trailed off there because expanding it's quite a bit. But if you look here, oh shoot, sorry, I erased some of that. It's kind of important. So essentially, we're left with these 2 equations. But what we can do is actually divide this into this. So then this is going to be canceled, and then this and this is going to be canceled. So we're left with actually V1i plus V2f. My bad. Why did I change that? This is 1. Sorry. V1 is going to be V2f plus V1i. 2i. See, notation gets really important here. I'm messing up for some reason. I'm not sure why. It's been a long day. This is called the relative velocity equation, and it's actually pretty important to doing elastic activities. So let's start off with an example here. So let me fold this up. So let's pretend here. A glider, a 0.15 kilogram glider, is moving to the right with a speed of 0.8 meters per second on a frictionless horizontal air track. The glider has a head-on collision with a 0.3 kilogram glider that is moving to the left with a speed of 2.2 meters per second. Find the final velocity of each glider, magnitude and direction. Well, it's a horizontal track. It's not going to be going up. So for one, we're just going to look at things in the x direction here. X, y, x, y. Well, it's going to the right. This is 0.15 kilograms. It's going to the right at 0.8 meters per second, and this is going to the left at 2.8 or 2.2 meters per second, and this is 0.3 kilograms. Here, we don't really know where it's going, so it has some velocity that we don't really know. So how do we do this? Well, the first thing we can do is use conservation of momentum. So I'm going to erase all that because we're going to need it. So essentially, let's get on work. So it's going to be M1 V1 initial plus M2 V2 initial is equal to M1 V2 or V1 final plus M2 V2 final. When you look at this, it actually becomes, plug in the numbers that were given, it's going to be 0.15 times 0.8. I'm not going to include the units because we don't have enough room here. Plus 0.3 negative 2.2 is equal to 0.5 V1 final plus 0.3 V2 final. So actually, when you calculate this out, let's also divide out this 0.15 because it's divisible into this. So it's going to be V1 final plus 2 V2 final. Let's plug this in. It's going to be 0.15 times 0.8 minus 0.3 times 2.2 divided by 0.15, which is negative 3.6, and that's going to be meters per second. We could also use the relative velocity equation. So it's going to be V1i minus V2i, just rearranging the equation we had from earlier. V2 final minus V1 final. And then this leaves us with 0.8 minus 2.2, or plus 2.2 actually, and it's going to be minus V1f, V2f, plus V2f. Well, we can actually add this to this, and then we'll get ourselves the answer. So that's 3. So if we add it together, it's going to be negative 0.6 meters per second is equal to V1 final is going to cancel. So it's just going to be 3 V2F. We actually see that V2F is going to be negative 0.2 meters per second. And then we just plug it back into here. We have your V1F is equal to negative 3.6 minus, minus, so it's going to be plus 0.4 meters per second, which is just going to be negative 3.2 meters per second. And there we go, that's the answer. Well, if you wanted to write it out, we would say that the second glider is moving 0.2 meters per second to the left. The first glider is moving 3.2 meters per second to the left as well. But we don't need to do that. We're not submitting this to a test. Now the second collision type that we're going to be looking at is inelastic. And that's when, this inelastic is when it's not, when kinetic energy is not conserved. But particularly, we're going to be looking at a special case, which is called completely inelastic. And that happens when the objects collide and they just stick together. So in other words, let's pretend something like this is happening. This is the initial state, and this is the final state. Well, they're going to collide and actually combine together and start moving this way. Pretty sick. Because when this happens, we get a free equation. We get that the final velocity of both blocks are the same. So we can just ignore one of this little subscript here and just call it the final velocity. And if we plug this into our conservation of momentum equation, we actually get v final m1 plus m2, just because we can factor out the v final from the right side. And boom, this is another equation we have here. And this only has 5 unknowns. 1, 2, 3, 4, 5. 5 unknowns. So let's do an example. A 5 kilogram bullet is fired horizontally into a 1.2 kilogram wooden block resting on a horizontal surface. The coefficient of kinetic friction between the block and the surface is 0.2. The bullet remains embedded in the block, which is observed to slide 0.31 meters along the surface before stopping. What was the initial speed of the bullet? So, okay, first off, if the wooden block is resting initially, that means this is 0, right? And we also have coefficient of kinetic friction. We also have a slide, and that really makes me think. So we have something with a force and something with movement. First thing that pops into my head is going to be work, because work is integral of F dotted with dr. Or another, we can just make it F times delta R. And that's going to be really useful in this situation because we still have we have one unknown and one unknown, so 2 unknowns. So let's use this. So here we have bullets and here we have block. So it's moving, and this is going to be 0.005 kilograms, and this is going to be 1.2 kilograms. And it's moving at some initial velocity. And this is the initial state. And then the final state we have here, it's going to be both embedded in the block. So it's going to be 1.205 kilograms, and it's moving at some final velocity that we need to find. Well, the first thing we do, since we're given the coefficient of static friction, the first thing we should probably do is draw a free body diagram. So free body diagram. First we have in our coordinate system, there's going to be a normal force. There's also going to be friction because it's moving. And we're also going to have mg here. So doing the sum of the forces, we get here that n is equal to mg. And that's really all we need for this. We don't want to go into acceleration because that's not really necessary here. We're going to use work energy here. Particularly, we're going to use work total plus K1 plus U1 is equal to K2 plus U2. Essentially, what this says here is, well, we already know what this means, but essentially it's just basically how energy is conserved. Yeah. So, since energy is being lost to the surroundings, if we take away, if this is obviously going to be negative since friction is going this way, but the object's moving this way. So in the end, it makes it negative. So this is the work lost, and then that's going to decrease the amount of initial energy there is, and that matches it with the final energy. It's pretty useful. But this is of the block with the bullet in it. So when it ends, it's going to be stop. It comes to a stop, where there really isn't a change to a kinetic energy. This isn't a delta U. So end up with this. So we end up with 1/2, why did I make that one so weird? We have here 1/2 m1 v m total actually v final squared minus the coefficient of static friction times nd. So the friction is going to be friction d, but friction is mu n, so it's going to be mu n, which is just mg, and it's going to be m total times d, and that's equal to 0. So when that happens, we can solve for v final. So v final is going to be square root, well technically it's going to be plus or minus, but we'll see in a bit, m total. The m total actually cancels out when we bring it to the other side, so it becomes 2 mu g d. So if we solve right now for this, just because why not, it's going to be 2, 0.2, 9.8 meters. Well, I'm not going to put in, why not? Times 0.31 meters, because that's how much it moved along the surface before stopping. Well, plugging this into our calculator, we get here 2 times 0.2 times 9.8 times 0.31 square root. It's going to be 1.102 meters per second, because meters squared over seconds squared square root is going to be meters squared, meters over seconds. So we know this is, what sign is this? Well, if we remember, this is going to be our positive and this is going to be our negative. If something hits something like this, you don't expect it, with this being at rest, you don't expect it to go this way. That isn't really possible. So it has to go this way. So it has to be positive. Good, so now we have our conservation of we have the other unknown we can solve for the last one. So it's going to be m1 v1 initial is going to be vf m1 plus m2. So in other words, v1 initial is going to be vf m1 plus m2 divided by m1. So then, in other words, v1 initial is going to be equal to 1.102 times 0.005, 0.005 plus 1.2. And then, if we plug this into our calculator, we have here times 0.005 plus 1.2 divided by 0.005. And that leads us, v1 initial is equal to 266 meters per second, if we round. And yeah, that's inelastic collisions, and that's just momentum in general. So I hope you learned something from the day. I know this is just review, because I know school for some schools are starting off again. So I just want to give everyone a refresher. So I'm Blake, and signing out.